What is up, guys? Patrick here, and today I'm going to be teaching you all about OpenRocket. Alright, so first I'm just going to go over kind of what OpenRocket is. Essentially, it's this big open source project that was done by, I think he's Finnish, this like Finnish man. So because it's open source, all the code is publicly available. So if you want to go, if you kind of hate your life and you want to go sift through that, you can. This is the GitHub page here, and then within it, within the doc folder of that, he's got his thesis, which you can see here. Kind of goes over all his math and all his thinking behind this wonderful creation he's blessed us with. So to install OpenRocket, you can just search for OpenRocket. It's on this website here. You can go straight to the download page. And yeah, you've got all these options here. I'm just going to go with this one. Once it's downloaded, it's pretty self-explanatory. So when you first open OpenRocket, you'll get this like pretty blank window, and it's going to provide us a space to build our rocket. So the reason we use OpenRocket is primarily because it gives us this really good graphical user interface. So it's really easy to visualize the rocket as we're building it. So you've kind of got this section, this big section down the bottom here. That's where the rocket's going to appear as we build it. So it's empty as of right now. Then we've got this add new component region where we can see kind of all the components we might need are listed. And then this is kind of the rocket overview here, where as we add stuff, they'll appear in this list in the order they appear on the rocket. Makes it easy to select different components, because as you build more and more complex rockets, sometimes there'll be a bit of overlap. So when you're ready to create a new component, you can just choose from this menu here. A lot of them will be grayed out because they've got to be attached to existing components, which we don't have as of right now. So let's start with a body tube. Very similarly to all the other components, once you click on that button, you'll be met by this menu. Here you can adjust things like the length, your inner and outer diameter, the material that the component's made out of, and even the finish of that material, so how rough the surface of that material is going to be. As of right now, we're just going to be building an L1 rocket, so it's not going to be too big. We will make this 30 centimeters for now, and this outer diameter and inner diameter, we'll just keep it the same. And let's pretend we're using a PVC pipe here. We'll just stick to the normal component finish for now. So interestingly, we can override some of the components here, because our mass is going to be derived from the component we choose. Sometimes, after we measure things, we realize that this isn't so accurate, or we're using material that maybe isn't listed here. So through this override menu here, we can actually override things like the mass, the center of gravity, and the coefficient of drag, which we'll go into these things a little bit later. But yeah, it's just useful to know that you can do that. So we've got our body tube here. Next, we can just go ahead and add a nose cone. So again, we're met by a very similar menu. Here we've got a couple of options for the shape of our nose cone. Again, I'm kind of just explaining how to use OpenRocket. I'm not going to go into, why we use these different nose cones and what they mean. So again, we'll just leave it at 1. I'm happy with that length as well. These diameters, can be changed. Of course, we want it to match the diameter of our body tube. So, which was 5 centimeters. Oh yeah, also you can change units here. So just by clicking on the units, you can kind of change which units you want to use. Very useful. You'll have some options like to do with the shoulder. So that's yeah, you can see this part kind of extending at the back of the of the nose cone here, which essentially is going to insert into our body tube to help keep the nose cone in place. You will need shoulders in your L1s for your nose cones to keep them in. If you want to sim that, you're more than welcome to here. Again, we've got the override conditions, appearance stuff, comment stuff. Yeah. Also, if you click up here in the parts library, you can get a bunch of pre-made nose cones, which, we probably won't be using, but this menu will come in lots of use to us a bit later. So you may notice there's a little something wrong with our rocket at this point. We don't particularly want our nose cone on this side of the body tube. So again, in this menu here where we get an overview of the rocket, we can really easily just drag stuff around and rearrange it, and there we go. It's looking more and more rocket-like. Oh yeah, also when attaching components, you just want to make sure you've got the component you're attaching stuff to selected. So here, we'll attach some stuff to the body tube, and you can see a lot more of these options have lit up for us. So we'll start by going into the mass component. It's a very, very simple but very useful thing. Essentially, it is literally just a block of mass. So, we could make it 500 grams. We can make it, as long and as wide as we need it to be. And this could act as our ballast, which is just weight we add for the purpose of it being weight to the rocket, usually used to improve stability, or can also be used to represent different elements. So when we're simming the big rocket, we actually use mass elements for things like the nose tip, ballast, of course, and the air brakes, because there aren't air brakes here, and it's easier to approximate it to this big block. So as of right now, I don't think we'll need any ballast, but yeah, very useful to know. You can also move it with this slider here, and it can be moved relative to the top of the parent component, which is the component it's attached to, the middle of that component, or the bottom of that component. Which, yeah, this only really matters when you start moving stuff around, because it can get a little bit tricky when making sure things stay where you want them to as you move their parent components around. But we just won't bother adding any mass. All right, so the next component we're going to add is called an inner tube. Essentially, what the inner tube does is hold the motor in place. It's a tube that lies within the body tube that the motor is just going to fit super snugly inside of, and it'll allow us to kind of center that motor within the body tube without having to actually attach any components to the motor itself, but we can instead just attach them to the inner tube. So let's make our inner tube, just a little bit smaller than our body tube. And then the inner diameter, especially when writing sims, for all intents and purposes, is going to be equal to the outer diameter of our motor. So I've kind of skipped ahead, and I know that the outer diameter of our motor is 38 mil, or 3.8 centimeters. So I'll just put that in now, and we'll just make it about that long. It's really not too important, and we can resize this later. So again, we could move it around if we want, and we can change the material, which we will. We'll just set it to PVC again. I know when I did my L1, I used a PVC pipe as my body tube and as my inner tube, so very realistic here. The appearance ones, I don't think I touched on this previously, but they're pretty useful, when you can change the color of the component, just to kind of make your rocket easier to look at, I suppose, for someone coming in that doesn't really understand that, maybe you've used a mass component to represent air brakes, so you'll make it a different color to make it clear that this isn't ballast, but these are actually air brakes. And you can also rename elements to improve the readability. So we've now got our inner tube, body tube, and nose cone. Next, we'll add some centering rings. So what centering rings do is hold this inner tube in place. Hold the inner tube in place within the body tube. So you can see it automatically does this stuff for us, which is great. We've got 4.6 centimeters as our inner diameter of the body tube, and 4 centimeters as the outer diameter of our inner tube. So this is essentially going to be a ring that's the inner tube is going to sit inside of, and the body tube is going to sit on the outside of, and it just makes sure everything fits nice and snug. And then you'd also make sure it was attached. You wouldn't just rely on friction, hopefully. So again, OpenRocket kind of just does this stuff automatically for us, which is great. You are able to change it. You just untick the automatic stuff and adjust these sliders as needed. If you're going to the TCS to make your L1s, you'll have access to a lot of different materials that you can use. In this case, let's just assume that they're going to be birch wood. Finally, we just want to move them around. So we're going to have quite a few of these. I'd say 3 is probably a good number. You might want to take a bit more care when distributing these. Make sure they're somewhat equally distributed along the inner tube, but for now, we'll just create that one there. So what we can do is right-click it and duplicate it a couple times. Double-click to just go back into it and move these along so that they're somewhat evenly distributed along the body of or along the inner tube, rather. So now we've got our inner tube. It's nice and centered. It's going to be held in place. We've got the body tube, and we've got our nose cone. Next, we're going to go over the bulkhead and engine blocks. So these are somewhat similar. I'm going over both of them because we probably won't be using bulkheads in our L1s, but we'll be using engine blocks, which kind of act as bulkheads. So what a bulkhead is, they essentially separate different sections of the rocket, and they'll act as this structural element that we can kind of tie things to. In our bigger rockets, we've got big metal rods kind of attached to them, and they're very, very vital structural elements. But in this case, we're going to use something called an engine block. So what an engine block does is essentially act as a bulkhead, but it's got a hole through it. And the reason we need that hole is that once our motor burns out, it's going to ignite a fuse, which at the end of some period of time will let off a black powder charge, which will kind of blow the nose cone off of our rocket and hopefully send our recovery system out through that hole, and then deploy it. So because we need this charge to actually get all the way through here, we're going to use an engine block because it's got that hole in the top, which will allow all that fun stuff to occur. So we'll move that along to be around the top of our inner tube here. Again, they've been nice enough to automatically set the outer diameter for us, and then our inner diameter, it'll vary for each of us, especially given the motor, but I'm just going to set it at 2.5 centimeters here. That should be more than enough. Importantly, especially if you're making your L1s, your smaller scale rockets, we want to make sure we've got room on these two sides here to attach some way for us to ensure our parachute is going to stay attached to the body after deployment. So if we don't do that, we'll shoot the parachute out and it's not tied to anything. I'm sure it'll come down nice and slow, but our rocket, on the other hand, will not. So we don't want that happening. And then finally, as the jump cut you just saw may have alluded to, we're going to be changing the length of the engine block. So again, because this is a structural element and we're going to have our recovery system tied to it, we want to make sure it's long enough that we can get some screws through the side here. To hopefully tie our recovery system to. So I'm going to make mine massive, which is probably about 1 inch. Yeah, we'll just make it 1 inch. And that'll make sure, we've got enough room and that, our recovery system won't fly out when the charge goes off. So the rocket appears to be coming along nicely. Now, whilst we're on the topic, I'll go into our recovery system. So here we've got our parachutes. Again, in our larger scale rockets, we're typically using 2 parachutes, a drogue chute to kind of slow the descent a little bit without allowing the rocket to drift too much before deploying a main a little bit closer to the ground. These L1s shouldn't be going too high, and we'll be sure to track them all, so that won't be an issue. So we're just gonna have one nice big parachute. I believe we've got ones that are about 30 centimeters. There's some that are less, there's some that are more. This is fine. We'll just go with 30 centimeters. Ripstop nylon also works. It's probably a bit better than crepe paper or office paper. So yeah, we'll go with ripstop nylon for now. So that is our material and canopy dealt with. Again, shroud lines is those are all the cords attached to the end, like the circumference of your parachute. This will be very, very dependent on which parachute you end up choosing. Last time, it was very much a first come, first serve thing on the day when it came to parachutes, so there wasn't too much direction. You may not be able to sim all this stuff beforehand. What's important is that you ensure you've got enough space for like a realistic sized parachute. This one's 30 centimeters when deployed, so when we fold it up, like if I account for a 5 by 3 centimeter footprint, and then this is the diameter, so 5 by 3 by 3 area or volume for my parachute. I will assume, actually I'll make this even longer. If I go 7 by 3 by 3, I assume we've got more than enough room to play with here when packing our parachute in. We can also set deployment times and stuff, but our motor kind of deals with all that, so we can again just leave that alone. Hey guys, it's Future Patrick. Next in the video, I went into shock cords, and I just kind of talked for way too long. This video is already really long, so thank you so much for sticking by. And yeah, I don't think I needed to talk for as long as I did, so I'm just gonna talk a lot quicker this time. So I'm just gonna add back a engine block and a fake parachute. Which yeah, we can just store it there. So essentially what our shock cords do, they keep our parachute attached to the body and the nose cone of the rocket. So we're actually going to have 2 lengths of shock cord. Those of you with an amazing memory and who attended the Intro to Rocketry session might remember that your shock cord should have a length of between 3 to 5 times the length of your rocket. So that's cumulative. So if you sum up the length of the stuff in the nose cone and the stuff in the body tube, it should end up around 3 to 5 times the length of your rocket. So if I add a shock cord here, when packed, it's going to be, it'll be something like that. It'll be attached to both the parachute and the engine block, which is what we're tying it to, or attaching with a carabiner or something like that. We want this length here, to be, we can make this one, this is just shy. Now it's exactly 3 times the length of the rocket. And then we're going to add, or you would attach the other section of shock cord to your nose cone. Typically, probably, you can see I've added in this shoulder that I talked about previously. It'd probably be tied across the shoulder or tied up right where the shoulder ends. You'd have a little section that goes across your nose cone to tie your shock cord to. And we can just make this one, not too important. I'll make it 60 centimeters. So we're well within that 3 to 5 times body length region. So you also want to account for the packed length of this cord. I've got 60 centimeters of cord here. Do I think I could get it into a 4x3 by 3 centimeter thing? I don't know. Probably not. So I'd probably make it a little bigger, and then same for this one. Just make it a little bigger. But yeah, that's essentially all that shock cords are. That's all there is to them. And yeah, I'll let you get back to the old Patrick. Yeah, so the rocket is slowly coming together. Next, I reckon we add some fins. Get this thing actually looking like a rocket rather than a fancy pencil. So we've got a couple of options for fins. We've got trapezoidal, elliptical, and freeform. You're welcome to choose whichever you please. Trapezoidal ones are easily the easiest to work with. And yeah, just make a lot of sense in this case. So we're just gonna use trapezoidal fins, but please feel free to explore the other options. I will actually quickly show the freeform fins because they're pretty fun. You can use this shape tab on the freeform fins and kind of just build any shape you please. And you can get some really funky fins going. But for now, we're not gonna have fun. Because we're very serious here, and we're gonna stick to trapezoidal fins. So here we can adjust the number of fins on our rocket. So let's go with 4. We can change the root coordinate of our fins. So that's this front part of the fin there at the base where that attaches as a distance from the base of the rocket. So it's 0, it's going to be at the base of the rocket, and we can move it along here to essentially make them longer at the base. So we'll make them a little longer for now. We'll just make that 6 centimeters, and we'll actually move the tip cord so that it is in line with the base of our rocket here. So we haven't got anything extending below the base of the rocket. In this case, that was 3.5 centimeters. Finally, we can change the height of the fins so we can make them a little bit longer or a little bit shorter. Why don't we go with 4 centimeters here for now? Finally, you can change the sweep length, which is this line that kind of runs up along here. If we make it longer, you'll notice the angle also changes. So these guys are codependent. You can change either one to make it make sense. Finally, you can change the cross section of our fins. So you've got a couple shapes here as to what our fins actually going to look like from the back or from the front. Again, I will highly stress that you can just go for square fins here. There's no reason to do an airfoil or rounded. Rounded wouldn't be too hard, but again, you'll probably be using resources over at the TCS and doing laser cutting there, and it'll just be really easy to quickly cut out some fins and not have to worry about it. We can, however, change the thickness of them. I'm not sure how thick the MDF, which is the material, or they've got 2 options for thickness for MDF over in the TCS. I'm not sure. I don't remember what they are. We're just going to go with 0.5 centimeter right now. So again, we can move them up and down along the body, so we can do a lot of funky stuff there. I am just going to leave it at the base. We can also add some rotation, but that doesn't really change too much. It's more of a perspective thing. Or if you were, adding elements that only appear on one side of your rocket, then maybe it'll play in. But for us, we can just leave that at 0, make our lives easier. And this time, let's go with some quantum tubing. for our fins. Please use the correct material here. Those densities change pretty significantly, and will play a big role in your stability. If you see here, we've got 0.877, and then if I go up to PVC, it'll drop, and if I go up to something lighter like pine wood, we get a lot more stable. And I'll go into a bit of detail as to why that's the case later. Finally, we've got fin tabs, which are essentially little sections of the fin that extend down into your body tube. That's how you'll attach them to your body tube. It's very similar to the shoulder for the nose cone. We'll just make them nice and short here. This isn't really necessary for simulations, so we'll just leave it as is, but just know that's an option. And when we do the boat tail on the big rocket, it just allows us to kind of extend the fins in to a desired distance very easily and not have to worry about dealing with all of that. All right, so now the rocket's kind of coming together. It's looking pretty cool. We are just gonna add a couple more things. So we're gonna add these things called rail buttons, which we will probably just be 3D printing those for you guys. Once we figure out how many L1s are gonna be made, we'll make sure to have all those printed, and we'll be good to go. So essentially, what rail guides are these little knobs, as you can see here, on the side of your rocket that'll make sure it stays attached to the rail that it's launched off of. So we'll just make them a little smaller because this is kind of insane. Okay, and we'll make it look something like that. It's honestly not too important, especially if you can get that, get the height of it down, and probably the thickness of it and length of it. You're good to go. Like, this is really it's gonna add a bit of drag, so you want to make sure you're adding them. We're gonna add 2 instances. We're gonna have 2 rail guides, and we can change how separate they are. We'll line them up something like that, and then just shift them up. So we've got our 2 rail guides. And with that, I believe the rocket's complete. We are just missing a motor. Now, before we go into the motor, I do want to touch on one final component, which is the tube coupler, which we will not be using in this particular rocket. Essentially, it's how we attach 2 body tubes together. It's going to have, an outer diameter pretty much equal to the inner diameter of your body tubes. It's literally going to be this tube that they both slot onto to hold them together. So very, very important element when building bigger rockets. Probably not going to be used in our L1s because, again, our nose cone is going to have that shoulder that's going to keep it, it's going to allow it to slot into the body tube very similarly. So once we're ready to add our motor, we can head over to the motors and configuration page. So note, you can kind of do this whenever you please. In a lot of cases, I'll get the body tube, get the inner tube in, and then add the motor, and then I'll build around that. I just thought it would flow a bit better if we did it at the end. So on the left here, in this motor mount section, we can choose where our motor is going to be attached to. We've added this inner tube, so it's going to be attached to that. So we'll click on that, and then we can click this select motor button, and we'll be greeted by this beautiful menu of billions, probably not, of motors that we can choose from. So they go all the way up from A-class motors up to O-class motors, which O-class motors are what we flew our last Spaceport America Cup rocket on. So, we're at the upper end here. Our L1s are going to sit in this region here. So I am going to narrow us down to the H-class motors. I believe all the ones we ordered were H-class motors. And let's go with something a little more chill. Let's just go with an H100. So we'll go with this one here. slot it in, and we can see, it kind of fits nice and snug inside that inner tube because the diameters will match up. So you'll notice we've got a bit of a length mismatch here. That's fine. As long as this tube, you actually want it a little bit longer. This is probably a bit too much space, but we will make do. It's okay. And yeah, we've now added our motor. It's super easy, just like that. It's been slotted in. So before we go and fly the rocket, you'll notice this measurement labeled stability here that I've touched on a couple times. And as we've added components to the rocket, it has danced around, and it's currently sitting just above 0. Now, I think even without any knowledge of rockets, if I told you my rocket had 0 stability, you'd probably get a pretty good idea that that's not good. We don't want our rocket to be sitting at 0 stability. And it's also important to note that stability isn't a more is better measurement. We don't want our stability to be as high as possible. We kind of want it to sit in this region of, I believe it's like 1 to 2 is like for your L1s. If it sits between the 1 to 2 region, especially around that like 1.5 region, you'll be good to go. So we've got to do some stuff to get the stability up. But if I'm pretty content on this design, and I don't want to change any lengths, I don't want to touch any of that stuff, there's a couple of ways I can still adjust the stability of my rocket. So the way stability is measured is the distance between your CG and your CP, which represent center of gravity and center of pressure on the surface of the rocket. And that, with that measurement in a ratio with the diameter of your body tube. So if we want to increase stability, we want our CG and CP to be further apart, with the CG closer to the nose than the CP, or else we'll get negative stability when they cross and go the other way. So if we want to move our center of gravity further along the surface of the rocket, or further along the rocket, one pretty typical way to do that is to add mass to our nose cone. So because this is, of course, a center of gravity or a center of mass, the further away we add the mass, we'll have a greater torque. We'll be adjusting the CG by a greater margin. So we'll typically put it right in the end of the nose cone there, so that we don't have to add as much weight and we can still move the CG a ton. So if we go back to our trusty mass component here, and say we'll throw 100 grams in. So for reference, again with my L1, I threw a couple nuts, the metal nuts, into the tip of my nose cone, filled it with hot glue, let it dry, and that was my nose cone ballast. So 100 grams should be a nice amount to throw in there. We'll make it a little more realistic. It'll probably look something like this. And yeah, and to demonstrate, this whole further away from the CG the better thing, you can see here, as I move it closer to the CG, stability is going to go down, and the further away I move it, the better. So we want that as far forward as we can get it. All right. So we are above stability of 1, which is lovely, but I reckon we should probably get our rocket even more stable. So another way we can do that, besides adding mass, we could make our rocket longer. So if I just make it longer here, you'll notice our stability getting really, really, really good until we're way overstable. Now, that works for a couple of reasons. Again, we're moving all this mass even further away from our CG. We're also playing with the center of pressure a little bit, or not a little bit, but we're playing with our center of pressure when we adjust that. So that is one way we can achieve that. Another way would be to play with our fins. So you can see here, if I simply play with the height of the fins, the bigger I make them, the higher our stability goes. And actually, if I move this a little bit, so we can actually see, you'll see as I make them bigger, our center of pressure is going to go further and further back, closer to our fins. So if I, increase their height, I believe they were sitting at 4 before, and I make them 5 centimeters tall instead. You can see now our stability is looking pretty good. Now, interestingly, by moving, our root cord around, and you'd think increasing the area of our fins, you'll see that our stability is actually back down to what it was previously. This is because we're increasing the volume, we're increasing the area of our fins, but we're also moving that area closer to the CP, so it's not actually changing the center of pressure a whole lot. So that's a bit more of a difficult approach when playing with fin size. Whereas increasing height, you're not really moving the width, you're just going to increase the height, and it's always going to move your center of pressure reliably. And we've got that stability of 1.4, which is looking all right. I might actually just increase a bit of mass here, so we've got, it's a bit much. So we've got a stability of 1.5, which is great, and our rocket's looking ready to go. So in the bottom left here, we can see we've got a projected apogee, which you may have noticed had been changing this entire time as we built the rocket. So this one's going to go to about 1 kilometer high. It's going to go 0.72 times the speed of sound with a max acceleration of 190 meters per second, which is awesome. We've also got the weight and our diameter and our length, all those great measurements, super easy to access. But let's go run some simulations. Hello, it's Future Patrick again. We're now just going to cover some simulation stuff. I, again, just yapped way too much on that side of things. So I'm going to go over it really quickly, really briefly, with the Florence simulation. So this is a rocket we took to the US, which, I can also actually just briefly show you all these, you get the back view, you can get a 3D figure, all this really cool, these cool views. But I just find that this is the easiest to process. Anyways, if we head over to simulations, you can see we've got a couple of things set up here. You can have different motors, and thus you get all these different stats to do with the rocket. So let's get a new simulation going. We're going to use this the O5500, which is the motor we launched on. Here you can see we can adjust the wind, so we can we can do 4 meter per second winds. You can add a standard deviation in the wind speed, which is pretty cool. It'll account for some changes there, but we'll just leave it as is. You can also throw in some turbulence, and then of course the direction of the wind. You can also set atmospheric conditions, which it's pretty typical to just use the international standard atmosphere, but if you know the temperature on the day and can derive a pressure, or you have a barometer, this makes a big difference in your results, but we'll leave it as is for now. We can also set the location and our elevation, which will play into the atmospheric model we use, and then we can also change the launch rod, which I believe I'm not going to get this perfect, so we're just going to say it's 360 centimeters. I believe it was just a little bit more than that, maybe 364, I think, the launch rod for Florence when we were in the US. So you can also change the model of Earth, the approximation we use. Earth's not a perfect sphere, but we can approximate it to one pretty well. But you could also use a flat Earth, or I'm not familiar with this one, but I'm assuming it's an ellipsoid that is shaped closer to what Earth actually looks like than a sphere is. But this shouldn't matter too much, really, with any of the simulations we're running, but particularly the L1s. And then you can also just adjust the time step between measurements that you receive through your simulations. It's also cool to mention that OpenRocket allows for extensions. This is one of the many amazing features afforded to it due to its being open source. It's really easy to modify. So there's a couple extensions you can find around for better simulation stuff, or even, don't quote me on this, but there may be some air brake compatibility. Anyways, if we're happy with these conditions, we'll say it's really intense. Yeah, we'll just double it. We'll keep it at 4. We've got all these conditions. It's awesome. We can simulate and plot. So you can see simulation 17 just appeared down here. Our apogee's, been altered quite significantly. We're going a bit slower off the rod. We reach apogee faster. Our max velocity is less. Obviously this wind played a bit of a role, which is really cool to be able to see. So what we can then do is either plot or export the data. So I'll start with the exporting because we won't go too much into that today, but essentially you've got all these variables and you can just export a CSV of them as you please. So it's really cool, very useful for if you want to analyze the data or verify your simulations elsewhere. And you can just, all these things are pretty self-explanatory, so I won't go into them, but I'd be happy to explain them to you if you were interested. Now we can also do plots inside of OpenRocket. So there's a couple of preset plot configurations. Vertical motion versus time is kind of the default. You'll get your altitude, velocities, and accelerations in the Z direction, Z direction, so like upward direction, which is awesome. And I can click this and plot, and we'll see here we've got a nice graph going. I'll actually move my big head so you can see when our big parachute comes out how much slower we descend compared to our drogue, which is out for the majority of our descent, until we hit this, I believe it's just under 1,000 feet. Yes, so something to consider with your L1s and with any rocket you're designing is this section here, where we can see we hit apogee and then we deploy a recovery system. Now this graph's going to be scaled down a lot for your L1s. There's a couple seconds between these moments here. It'll be the same with your L1s. The important thing is to ensure that this deployment is always taking place after apogee, not whilst the rocket's going up, and that you do leave, a buffer of a second or two after apogee before your parachute comes out, because you can't if your sims aren't verified, you can't trust them. Maybe you got you miscalculated something, and then now because you set your deployment to be exactly at apogee, it's going to happen as the rocket's going up, which can introduce a couple problems. So yeah, just giving yourself a 1 to 2 second buffer between your recovery device deployment and apogee is going to be pretty helpful. The way that buffer is set, so essentially the way the motors work, is after they burn out, they'll set off, I've explained this already, I think, sorry to repeat myself, but they'll set off a fuse, which will, once burnt all the way through, set off a black powder charge, which will pop your nose cone. You can cut that fuse and make it a bit shorter. So, whereas if you're getting an issue where your recovery is coming out too early, you may have to rethink your rocket design. So you may, there's tons of factors that could be playing into why that's happening, but that's certainly a more rare case. They give you a pretty solid buffer on these ones. It's typically too long, to be honest. So in the interest of time, and again, thank you so much for persisting with me. we'll go over just a couple more of these. So we've got drag coefficient versus Mach number, which is what is known as a drag curve. So we can see the drag on the rocket as a function of its speed, you know, in Mach number, which changes. It's a whole thing, but this is based on the speed of sound, and the speed of sound changes with altitude because your temperature or your pressure, so your air density is changing. The probably important thing that you want to make sure you're always checking is your stability versus time graph. So we don't really need the center of pressure or center of gravity stuff. We just want our stability margin calibers, and I'll just turn all of these on so you can choose which flight events you want to count, but we'll just use them all. And you can see here we got a lot happening. These graphs are quite painful to use typically, but I'll try my best. So we can see, I can't get to the region I want to. We'll just view it like this. I'm sorry. So we can see our stability, which is that ratio we discussed, and how it varies over time. We can see that as time goes on, our stability is going to vary a lot. We want to make sure, and we want to look out for these moments in which our stability is at its lowest. So we can see here at the beginning of its flight on the rail, stability is not looking so hot. It's 1.5, which, with our L1s is wonderful. With this rocket is solid. So yeah, you want to make sure that you're not just looking at this or like an average stability, but we really want to account for the worst case, and we want to say when the rocket is least stable, how stable is it? Because that's when things go wrong. So once we've checked that our stabilities are all good as well, which we just covered how to handle stability, we should be good to go. A couple final considerations are your ground hit velocity, your velocity at deployment, and your velocity off the rod. So you really want to make sure your rocket is going, for lack of a better way to say it, fast enough off the rod. If it's going less than 15 meters per second off the rod, chances are something's wrong. I can't tell you exactly what, but these things are pretty fast, so you shouldn't have an issue getting speed off the rod. So if that's the case, you may want to rethink your design a bit. You may have way too much ballast. Maybe your rocket's way too long relative to the motor you've chosen, so you got all this drag on the surface. There's a bunch of factors that could be playing in. You also want your ground hit velocity to be somewhere between 6 and 7 meters per second, probably, is the sweet spot, especially for the L1s. We do it a little slower with the big one because it's very, very important that we get it in one piece for the competition. But anything, over 10, you're risking damaging your rocket. And because your rocket has to be reflyable in order for you to earn your L1, we want to make sure that we have the best chance at recovering our thing safely. So we can use a bigger parachute. We can reduce the mass of our rocket. Those are kind of the most common ways to ensure our ground hit velocity is all good. Finally, I think I was going to talk about the velocity at deployment, and optimum delay kind of plays into that. I talked about, cutting your fuses and making sure your deployment's happening at the right time. If you're going too fast when your parachute comes out, there's a higher chance of something going wrong. So again, you want that slight buffer, but assuming we accelerate back down to the Earth at 9.81 meters per second, and we've also got those drag forces counteracting that. If I put in a 2-second buffer, I'll probably be capping out at like 15 meters per second, which is certainly slow enough that we'll have no issues. Optimum delay is really fun. It just tells you like how much to cut your fuse essentially. If you've got a 14-second fuse, and it tells you your optimum delay is 7 seconds, you can be like, cool, I will just cut my fuse in half, and I should be good to go. So that's a very nice feature. Oh, yeah, very nice feature. But I believe that's everything. So I really just want to thank you for your time. I know it's probably been a drag to get through. Video wasn't as entertaining as I hoped it would be, but I hope it was as informative as you guys needed it to. And I'm always here for questions, so please don't be scared to ask. All right, see you guys.